Hello, everyone. This is Ben. I'm here to give you a quick overview of the notes that I would have presented if I wasn't sick earlier in the week. Just in order to get this out there as soon as possible, I figured I'd just go the easiest route, which is to just take my lecture notes, scan them in, and then make a PowerPoint video of going through them. So hopefully it will be very similar to the lecture experience, except I'm going to be going across it with PowerPoint, which means that contrary to how I usually run my class, as I described in the beginning, it's going to go a lot faster. So to make up for that, my intention is for you to slow down, print out the notes to follow along. You're going to need to print out the notes for week 5 and week 6. Pause in between, make sure you can follow all the steps. If you are very dedicated and want to go through, as usual, I highly recommend you handwriting the content on a separate piece of scratch paper or your own notes if you like. And hopefully it will be a close approximation to the actual session that I missed. So let's start out. As you see, we're going to pick up from where we left on in week 5. We actually went a little bit fast last time, which works out pretty well. You should be reasonably equipped to do the homework minus the extra bit in the end that I wasn't able to cover, which I will right now. And since instead of going into new material, I figured what I would do is to give you a really, really hard problem that goes over one of the Fourier series derivations for a signal. And we're going to go all the way to the final expression. I don't expect anything to be this hard to show up in the test, and something like this does show up in the homework, but it's going to be easier. So it's going to be a bit of a long drive, and it's going to be just one problem, a few parts, but the first part's going to take a while. It actually took a lot longer for me than I thought it would. But if you suffer through it and follow along with me on this journey, I think that you'll feel a lot better about doing a Fourier analysis from the ground up, which is something from recent discussions with some of you I hear that you're not too comfortable with. So let's start out by reviewing the steps that we went over for Fourier analysis in week 5. So I have the page number up here. I'm going to go over all the pages, but I'm zooming in and presenting it half a page at a time. But all the slides that are the top half of the page, I'll have the page number up here so that when you download the notes, you can go and look at it on your own sheet of paper in hopefully some kind of more readable format. But let's go through the steps real quick for plotting Fourier analysis, for doing the Fourier analysis. So step 1, like I said, is we're going to go use either method 1 or method 2, but the main output of a Fourier analysis is a formula for the coefficients AK and the fundamental frequency F0. After which you can optionally write it out in a table, but you now have all the information to draw out the spectrum like we did in the prior week, week 4. Now, moving further down the page, we're going to focus this week on method 1 since it's kind of the most rigorous method, and by now, through the last homework, you should have had a bit of practice in method 2. So when I said the really heinous problem, we're going to do method 1. The nice thing about method 1 is there are only so many different waveforms where this works on. So once you've done a couple of them, you probably have done a lot of the ones that you can possibly be tested on. So moving down the page, we'll start looking at method 1. Again, it's more general. This is how we approach all Fourier analysis, which means it's more work, which means it's less likely to show up in the exam, but they might still have you derive, say, 1 term or 2 terms. So the first step, we're going to find the fundamental frequency, which is 1 over the fundamental period, and the period is something that we can find one of 2 ways. we can look at the plot and find the smallest repetition interval, or we can find the greatest common denominator for all the frequencies present. So you should be somewhat practiced in that by now. One thing to note in this process is when you're selecting T0, you can choose any start-stop point. I'm listing T equals 0 to T0 in this case, but you can choose any start and stop point as long as you cover exactly one period. And we'll show you that in the example. A0 is something that we usually find separately because in the general form, sometimes you run into a singularity or divide by 0 situation for the k equals 0 term. So in that case, you can use L'Hopital's rule, but the other reason that we find this separately is because if you plug in k equals 0 in the general integral that we're going to use, you're going to get the expression for an average value or a DC value, which sometimes you can find graphically, and that will save you some calculus. Next step, step 4, which tends to be the worst one, is you find a general form for AK or a specific term if you were told to look for a specific term using this integral expression here, where you have 1 over T0, integral from 0 to T, the signal that you're trying to do Fourier analysis on, times e to the minus omega naught kt. Notice that once you integrate it and take the limits, you're not going to have t anymore. The only variable left is going to be k. Remember, omega naught is also a known factor. It's just 2 pi f naught or 2 pi over t naught, where f naught is the fundamental frequency and t naught is the fundamental period. So remember, your answer is going to be in terms of k, and sometimes you need to break it into parts because the function is piecewise continuous, as is the big scary example that we're going to work on today. The other thing to remember is that you can choose any beginning and end point here. That's convenient. Just make sure that it covers exactly one period. All right? So we're going to use method 1, and then we're going to do some follow-on problems. All this is going to be one example, and it's going to be bad, but like I said, hold on to your hats, pull out some scratch paper, follow along with me, and if you understand each of these steps, you should be pretty solid in the general Fourier analysis process. The other thing that I wasn't able to get to last week, but was in my notes, was the concept of performing basic operations, meaning if we did certain things in the time domain, what would that do to the frequency domain terms over here? So the general idea is if we have a new function y of t that's going to have some relationship with x of t, what does that in turn do to the Fourier analysis? So if the Fourier analysis of y of t ends up being a bunch of coefficients, which we'll call bk, how do we find bk by simply just tweaking ak? So I've listed a few of them. These were basically all the properties that were listed in Appendix C, and I just summarized them into this table here. If you scale it, meaning you just multiply the whole thing by gamma, then the coefficients in turn are just multiplied by gamma. So the new b of k is simply going to be gamma times a of k. If you add a dc component, as in you just take the function, you just add a constant to it, then if you think about it, that only affects the b0 term since you're just doing a bc shift. So all you have to do is change your b0 term to be a0 plus c, and then all of your other coefficients are going to be the same. Adding two signals is a bit trickier, where if they have the same fundamental frequency, then you can just add the coefficients together. However, if they have a different fundamental frequency, then it's going to be a bit trickier, because in that case, you don't even know if there's going to be a common multiple for the signal to be periodic and repetitive. But if it is, you're going to have to find the new f0, and you're going to have to do a re-indexing. Next up, time scaling is if you do this, if y of t is equal to x alpha t. And as you saw in the lab that we just did, it doesn't really change the coefficients at all. What it does is it changes the spacing between the coefficients, which is determined by the fundamental frequency. So what you have is the fundamental frequency changes, or in other words, the fundamental period also changes, but all the coefficients stay the same. Time shift is one that we'll do a bit, and we'll do in this exercise, where if you just shift x of t by a certain amount, and in that case, a shift in time is going to be the addition of a phase term as defined here. So if you shift it by td, you're going to add an extra phase of e to the minus j omega naught k td after each of your ak coefficients in order to get bk. So we're going to do that once we're through all the very heinous examples. Moving further down, there's one more property that, and a few notes. I won't go into as much detail for now, but when you differentiate it, since the only term in x of t in the Fourier series that actually has a t in it is exponential, you can see that the differentiation just gives you an extra multiplication of whatever the derivative of the exponent is. So remember, we have e to the j omega naught kt on top, so differentiating that just gives you an extra j omega naught k. So it's just some general concept is when you want a frequency shift by some frequency omega s in the frequency domain, that's the same as multiplying it by an e to the j omega st term. Or another way to look at it is, as you might have seen in your amplitude modulation lab and homework, when you want to shift a signal that was originally centered at frequency 0 and you multiply it by cosine omega st, then all that does is instead of being centered at 0 here, it now gets shifted out and is centered at positive omega s and negative omega s. And the power of the signal is basically split. So each of these is half as tall as the original over here. So again, moving on to the new stuff, I just wanted to really quickly review that Fourier analysis process that we did last week. We're going to do a worst case scenario problem for method 1 so that hopefully all the other problems that you'll see will feel like relative solid ground for you. And then once we have gone through all the hard work and come up with our answer, we're going to do some of the operations that you saw in that table and see what the effects of. So again, there are no new notes. Just make sure that you have the week 5 material as well as the printout of these notes on hand while you're listening to this. And we're going to work on the 1 week 6 heinous example together. So, are you ready? Here's the problem. We want to do Fourier analysis on the following triangle wave. It's a triangle wave that's centered at 0, so there's no DC value. The DC is 0, and it's going to go from 1/2 to negative 1/2, so it has an amplitude of 1, and the period I'm just going to generically define as T0. And in terms of the phase, it's going to be at its maximum point at t equals 0, and then it's going to go down, and then it's going to go back up. So there are 4 parts to this. The first is do Fourier analysis, which, as we mentioned before, consists of finding f0 and ak. And this is just to say do Fourier analysis, as in find an expression that meets this description here. So that's going to take some time, but again, pause the video and go through it slowly. Make sure you keep up with each step, and you should be pretty solid with method 1 of Fourier analysis. The second thing is we're going to shift it by 1/4 of a period, and we're going to scale. So we're going to define y of t is going to be equal to the original x of t, but shifted by t0 over 4 and multiplied by 2. For part B, I just want you to draw it. And for part C, we want to do a Fourier analysis for it by finding bk, where bk are the corresponding coefficients for this new y of t that we just defined. And the idea is to use the operations so that we only have to tweak the AKs that we found earlier and not do the horrible part A again. Finally, for part D, this is just a little bonus bit where we want you to adjust the signal so that it looks like this here. So it's shifted up, as you can see. So instead of going from 1/2 to -1/2, it now goes from 0 to 1. And the phase has changed a little bit. So we're going to call this signal z of t, and we're going to call its coefficient c of k. And I want you to find c of k. And then for those of you, I basically set this up because some of you might have seen triangle waves in the book and gone to look at it. And if you look at the book, you'll see that the answer is slightly different if you look at equation C20. So I want you to use the operations to shift the graph so that you change it from this to this, and then see what that does to the coefficients, and make sure that your resulting coefficients end up being the same as what was on the book, to make yourself believe that even though we were doing a different triangle wave, the answer that we got is valid and the same as what's in the book. So bear with me for part A, grab a nice warm drink and get comfortable. Off we go. So part A, the first step is pretty straightforward in method 1. Our goal is just to find the fundamental frequency. Here, the fundamental frequency is already given because everything was given in units of t naught. So the fundamental frequency, we'll just say, is 1 over t naught. Keep in mind that I'm going to use the term f naught and t naught, as well as omega naught, which is 2 pi f naught, potentially interchangeably just to save on writing. So don't get tripped up. Remember, we're still talking either about the fundamental frequency in radians or the fundamental frequency in hertz, or we might write it as 1 over the fundamental period. The next step is to find the DC value, which is going to be your k equals 0 A0 term. And in this case, it's really nice to just do it graphically. We know that there's no DC shift, so A naught is just going to be 0. So we can breathe a sigh of relief. One thing that I'd like to point out is, remember when I said that you can define your start and end points arbitrarily as long as it covers exactly one period? Well, this would be a really good example for that, because if I wanted to just simply break this down into 2 areas, a positive area and a negative area, so this is t equals 0. If I just kind of want to integrate it from here to here so I can see, hey, here's the first area, here's the second area, they cancel each other out, I can actually do that. I can just, for the purpose of generating this nice little plot, I can say, instead of integrating from 0 to t naught as I had in week 5, I'm going to integrate from t naught over 4 to 5 t naught over 4. So it's still the span of t naught, but if you look at that portion of the plot, it's going to look like this, where you can very intuitively see you're going to go over a negative triangle area and a positive triangle area. So when you integrate across both of them, you're going to get 0. So again, as long as it goes over one fundamental period, you're good. We just chose these limits because graphically you can see this area 1 and area 2 relationship here and here. So 2 ways to find it. One is graphically looking at it and looking at the areas under the curve, but the other thing is you can just see that this is a triangle wave with no DC offset. So the DC offset is 0, so A0 is also 0. All right, now we're going to do the fun part. We need to find AK for any generic term of K that is not 0. So I'm going to start out by just writing out the basic formula, where we have 1 over t naught, x of t, e to the minus j Instead of omega naught, I'm going to write 2 pi over t naught kt. Integrated as a function of t over one period, and in this case, I'm going to go from minus t over 2, t naught over 2 to plus t naught over 2. So we'll have two straight lines. Hopefully you have this printed out. If you do go back and look at the picture, from minus t naught over 2 to 0, you're going to have a straight line going up. And then for the second half, 0 to t naught over 2, you're going to have a line going down. So by looking at the picture, you can come up with the equation for the line based on the slope and the intercept. And we're going to break it up into two integrals to start. So AK is going to be equal to the first integral. We're going to go from minus t naught over 2 to 0. And the equation of the line for that portion looks like this, where we have a slope of 2 over t naught and an offset of 1/2. So you can look at the plot carefully to know that you can come up with this. And then we're going to multiply it by the exponential, which is the same here. The second term, the second part goes from 0 to t naught over 2. And it's a similar equation for the straight line, just a negative slope, so same offset, but we now have a negative slope of 2 over t naught. And then this exponential is the same as what was up here, integrated as a function of t. So because it's a piecewise continuous function, this x of t, we're going to split it into two pieces where it's two different lines. Next up, we're going to just distribute this, multiply this in, so that we get two terms off of this and two terms off of this. So 1/2 times this exponential is going to give you this term here. 2t over t naught times this exponential is going to give us this here. And then similarly, 1/2 times this exponential is going to give us this term. Minus 2t over t naught times the exponential is going to give us this term. So nothing fancy or worth noting so far. All we did was we used the piecewise continuous x of t to split it into two, and then we just multiplied the exponential in to get 4 terms, as you can see here. And in this stage, because my piece of paper is only so wide, we're going to split it into 4 and examine them separately. So let's just call this term A. We're going to call this term B, this term C, and this term D. So let's just start out by looking at A, since that looks somewhat harmless. So A is going to be 1 over t naught. Again, the same limits. We're just copying it down here. And so this is just a plain old-fashioned exponential integral. So not a whole lot of magic there. It's going to be what it was originally, but it's going to be multiplied by an extra term. That extra term is the derivative of everything that's up here. The inverse of what's up here. So up here we have 2 pi jk over t naught up in the exponential. So we're just going to invert that. So we have 1 over that. And then, as you can see, you can do some cancellation. The t naughts cancel, so that's a nice little first step. And then the integral's done. All we have to do is evaluate it from minus t naught over 2 to 0. So that's what I do here. I'm going to bring all this out, and the 0 term is just here. It's going to be 1. And then minus t naught over 2, I'm just going to plug this into t to get this mess here. And as you can see now why we have it as 2 pi over t naught over here, because now you get these nice cancellations. So the negatives cancel, the 2's cancel, the t naughts cancel. If you do some cleaning up, this is going to turn into 1, and then this term is just going to be e to the j pi k. And so one thing that you see here, and one thing that I did here between these two steps is I have the j in the denominator, and then remember 1 over j is equal to minus j. So I bring that j up to the numerator to cancel out this negative sign here. So now this term here is j over 4 pi k, and we have 1 minus e to the j pi k. Now this is a trick that you'll be using a few times throughout this class, but remember e to the j pi is what? It's -1. So you can simplify this as negative 1 to the power of k. So now we're left with this slightly simplified expression for part A. Moving on, actually, we're going to look at C next because C looks suspiciously like A. So maybe we can just hope for something nice to happen. So let's start out. We're going to write out that same thing, 1/2. Remember, it's going to be 1/2. The only thing that changes between C and A are the integration limits are different. So we're going to just write it out like this. We're going to do something similar in terms of pulling everything out, taking the derivative, and then having the exponential with these different integration limits. And now, with some cleaning up, you're going to see same step. We multiply it by n, and you're going to get e to the minus j pi k minus 1, which from following the step before is minus 1 to the k minus 1. Same thing on the outside as in A here. And you'll notice this is just the same thing as A, but switched around. So we can switch it back to factor out. So we'll factor out a minus 1 so that the order looks exactly like K. And voila, we'll see now this expression here looks exactly like what we had at A if you go back and look. So we find that C actually is equal to minus A, which means that the two terms cancel out, and all that work was basically so that we could ignore both terms in the future. Hooray! Next up, we're going to look at B, and B is going to be the slightly more painful term. So bear with me here, and once we get through this, the fever is going to break. So over here we have B is going to be equal to, I'm just going to write it out, 1 over T naught. Here are the limits. We're going to do that negative portion, the minus T naught over 2 to 0 portion. So this is just copied over. If I take everything that's not that's not the lowercase t out, I'm going to just have this coefficient here. And then in here, you see I'm in the form of t times e to the something t. So t times e to the something t, for when you were taking calculus, you would have to use integration by parts. Or another thing you could do is, to save time, you go to an integral table, which is what I'm going to do because this problem is hard enough as it is already. And if you look up an integral table, just look it up online, or maybe your grandfather has a book. You can look in the exponential section. You're going to find this identity where x e to the ax is going to be equal to x over a minus 1 over a squared e to the ax. So instead of a, let's just call that smiley face. So in this case, by comparison, I'm going to lump all this in and call that smiley face, and just use this formula here. So I have the same coefficient here, and I'm going to apply this formula, but instead of A, I'm going to write smiley face. So I'm going to get this expression here, evaluate from minus T naught over 2 to 0. So now it's just a matter of bookkeeping and not messing up. We're going to start with a 0 term here. So if you plug 0 in here, you're going to get 0 because of this t here. If you plug 0 in the second term, the exponential of 0 is going to give you 1. So you're just left with this 1 over smiley face square with that negative sign there. And then for the second term, we have minus T naught over 2. So we're going to just carefully put minus T naught over 2 in here. So you're going to get this expression here. And then you're going to have your minus T naught over 2 up here. So e to the minus, this is a smiley face, T naught over 2. And then this coefficient's still out there. So now we're just going to open it up and simplify it a bit. So we just multiply this 1 in to get this term. You multiply this term with this term to get this here. And you're going to multiply these two together to get that. So now we're down to 3 terms. And all that remains is to very carefully insert what smiley face was back in and not mess up. So I'm going to put in 1 over smiley face squared is going to be this term here, and then this term turns into this, and this term turns into this. And as you can see, you can do some cancellations, and let's see, the negatives definitely cancel out here, as do the t naughts and the 2, and you can do the same bunch of cancellations here. The one place to be really careful is to do this square correctly. So when you square it, this negative sign is going to go away, and you square this negative j, which is going to give you a negative 1. So the overall result of this is going to be negative. So in this case, that's going to cancel out this negative sign. You're going to get a positive number here. But in this case, you're going to get overall negative. So you're going to get a negative sign here. But otherwise, you just square everything that's in there to get this. Again, this is just cleaning up to get that. And then you square this term to get that. Being careful with the signs. Now, when you do all this cancellation, you're going to see, hey, look, I've got e to the j pi k again. So you know what to do with that. You substitute it with minus 1 to the k. Meanwhile, you also see that you have a bunch of t squares up top, which will cancel with this t square down here. And then this 2 will cancel, will cancel out with all of these 4s so that you're left with 2's in the denominator. So with a bunch of cleanup, you're going to end up with this expression here that has 3 terms. Now, when we're trying to look at D, one of the things that we can do to save ourselves some grief is that we see that D is very similar to B, except for a few differences. First, there's a minus sign, and second, the limits are different. So in other words, if I just write B as some integral from minus t naught over 2 to 0, and I just call everything inside there as a star, D is actually the negative of that, and there's these 2 limits. Well, remember, if you can flip the limits at the cost of adding a factor of minus 1, so I can actually flip these limits to get a negative 1, which will cancel out with this negative, and end up with flipped limits. So that's just a clever little trick to get rid of this negative sign and not have anything to worry about. And all I have to do is just change the limits. So again, going through this process, you can see that I can just copy my answer from B partway through, and when I'm evaluating it, I just have to make sure I evaluate a different limit. With that bit of cleverness, I'm going to copy this line here. So I'm going to start out by writing this out, and again, getting it into the form where we can use that integral table result. I'm going to define the same smiley face value, and this is exact same thing that we had when we were calculating B, except now we're going to have different limits. We're going to go from t naught over 2 to 0 instead of minus t naught over 2 to 0. And remember, these were flipped because we were trying to get rid of that negative sign. So so again, we're going to just plug in the zeros over here, and then we're going to plug in the smiley face over here. And you're going to see this is very similar to what we had for part B, except our t naught over 2 is positive instead of negative. Again, careful with squaring it. So we end up with this term here, and I left this open to square at a different time so that you can see we're substituting in the smiley faces. Same cancellations that occur when we were doing B in terms of the t naughts canceling, the 2's canceling, and then we're going to get the same kind of squared term here. So we're still going to have the t naughts canceling with the t naught out here. The 2's going to change all the 4's in the denominators to 2. and we're going to apply our e to the minus j pi k is equal to minus 1 to the k. So doing all that cleanup, we're going to get an answer that also looks very similar to b, just with a few sign differences. So follow along. Again, this is just very careful bookkeeping. The trickiest part is just making sure that you square this term correctly. And in general, if you do a different problem, just being able to recognize this opportunity here where you can substitute e to the j pi k with minus 1. Notice last time we actually had e to the positive j pi k, but since it's e to the j pi is the same as e to the minus j pi, we can still use this trick. So a lot of work, but thankfully we were able to recycle a lot of it from part B to get D, which is very similar. Finally, we're going to put all that together where, remember previously, way back when you were a lot more awake, AK is equal to A plus B plus C plus D, and we had found that A and C would cancel each other out, so now we're just left with B and D. And hopefully, we're hoping that things will cancel out too because they look very similar. And so I'm just copying out B here, and I'm copying out D here. And you'll notice that the first terms have the same sign. The last term has the same sign, so they add up. But the middle term actually cancels out because they have opposite signs. So we're going to add these together, and you're going to end up with this expression here, which gives you 1 minus 1 being from this term here, minus negative 1 to the k over pi squared k squared. This 2 disappeared because we were adding together the like terms, and that allows us to factor out. That gives us 2's here, which can cancel out with the 2 in the denominator. So we end up with this nice little expression here, and now the final step when you get here is you plug in a bunch of values for k and pray that you see a pattern. So in this case, we're going to put in k equals 1. You're going to get 2 over pi squared k squared. K equals 2, you're going to get 1 minus 1, so you're going to get 0 here. And 3, you get a very similar expression, the same expression as 1, and 4, you're going to get 0. So then you can summarize and say AK is going to be equal to 2 over pi squared k squared when k is odd. Otherwise, it's going to be 0. So now all we have to do is summarize everything that we found. So we have remember when we do Fourier analysis, we want F naught and AK. So F naught we have, it was just given to us. And AK we found is 0 when k equals 0. We did that first. And then in general, when k is odd, remember plus and minus, it's going to be equal to this. And when it's even, it's going to be 0. Now there's an observation. I didn't specifically ask any derivation on this, but this is an important concept that you'll see time and again. But x in this case, if you look at the picture, it's even, meaning it's symmetric about t equals 0. Another way to say that is that x of t is equal to x of minus t. And what that means is that AK is equal to A minus K. And remember, A minus K is equal to AK conjugate. So the only way for that to happen is if AK is all real, as you see here. And that also means that we can combine this all into cosines. Remember, if you have sines and cosines, sines are odd functions and cosine is an even function. So the fact that the overall signal that you're trying to model is even means that all you're going to need is the cosine terms. You're going to need a bunch of cosines to formulate it, a bunch of even basis functions. So I'm going to prove that here a little bit, where we're just going to write out this generic expression, and I'm going to separate that into the A0 term, the negative terms. So I'm going to write this as k equals 1 to infinity. And then remember, this is a real signal, which means that the negative side is equal to the conjugate of the positive side. So for the k equals minus infinity to 1, I'm just going to write k equals 1 to infinity, but instead of a minus k, I'm just going to write ak conjugate. And I have e to the minus, remember this minus here, j omega naught kt. and then the plus terms, so the k equals 1 to infinity terms, which is just your standard expression. But remember that since so the a minus k is going to be equal to ak conjugate, but we see that because a minus k is equal to ak conjugate, that means that a minus k is going to be equal to ak. So we can actually substitute ak in here. Once you substitute that in, you can factor it out, multiply the thing by 2, so you can add in a minus 1/2 here, and then you're going to have the inverse Euler expression for a cosine, and then you're going to be left with a bunch of cosine terms. So you can see that when the signal's even, two main take-homes that you can get is ak is going to be equal to minus ak, which means that all of the terms are real. All of the coefficients are real. And that also means that you can write the signal as a summation of cosines, as opposed to a mix of sines and cosines. For part B, we're going to do an operation. So I've defined y of t as 2x t plus t naught over 2, which means if you think about it, it's going to be scaling it by 2, and then because there's a plus sign, we're going to shift right by t naught over 2. So for part B, I just want you to draw it out. It's going to look a little bit like this. So it's going to look like a triangle version of a sine wave, as you can see. So and because we scaled it by 2, it now goes from -1 to 1 instead of -1/2 to 1/2. So for part C, you want to try to find an easy way to find out what the Fourier analysis of y of t is. So we're going to say y of t is we're going to call its coefficients bk. And what we'll do is we'll just take this x of t expression, the generic x of t expression that we have for the Fourier series, and we're going to perform these operations onto this summation and see what happens. So the idea is that whenever you're faced with this kind of problem, you have to demonstrate what this operation does. You apply it to the Fourier series of the original function, and then you muscle it so that it looks like this, and you do a comparison to find out what your new bk is. So we're going to go ahead and do that. We're going to take 2, and then we're going to also shift it by t naught over 4. So I multiplied this whole thing here by 2, and I'm going to add a time shift of t naught over 4. We're going to expand that out. So I'm going to multiply this term in here. And when we also substitute omega naught as equal to 2 pi over t naught, you see we get some nice cancellations. The 2 cancels out with the 4 to form this 2. The t naughts cancel. And you're going to be left with the original term is still here, but you now have this extra exponential phase term. So we're going to pull this term. This all simplifies to pi half. So we're going to j. So we're going to take this term and pull it out here. So you're left with 2ak e to the j pi half, and then everything out here is the same. So this is the same as this, is the same as this, which means we can compare them. So this was the expression for y of t. Remember what we're trying to do. So you can write it out as this summation here, and now we can simply compare to see what bk is. So bk is simply equal to ak times 2 times this phase term here. And remember, e to the j pi half, why? Well, that's j. So you can get this nice little answer where bk is simply whatever you had for ak, but multiplied by 2j. So all you have to do is just copy your answer from A, but with this factor in, you get this answer here, where you have 4j over pi squared k squared for when it's odd, and zeros for all other values of k. So that's the power of using these operations, is if you know what the basic coefficients are, you might be able to just tweak your way to figure out what the new coefficients are for the new function without this extremely painful thing that we did in part A. Now, one thing to note is that the function that was even is actually now odd. So I've written out the answer here. I'm just scrolling down a little bit on the page. But you'll see that x of t is now negative of x of minus t, meaning it's odd, like a sine wave. And what this means is that bk is equal to minus b of the minus k terms. And so remember, bk is going to be equal to, actually there shouldn't be a minus sign here. bk is also equal to bk and on the negative side, it should be equal to bk conjugate. So so this isn't a typo. So b of minus k is going to be equal to bk conjugate, remember? Because it's a real signal. So the left side has to equal the conjugate of the right side. So if you plug this in, what that means is a conjugate expression ends up equating to a negative sign. Well, why would the conjugate flip the sign of the value? That would only happen if the value was purely imaginary. So we'll take another. So if you plug that in, we'll say y of t is going to be this whole expression here. If we, just for funsies, we'll do something similar to what we did before. We're going to split it into these two here, and then we're just going to plug in this new bk value we have. So we're going to plug in zeros for when it's going to be 0 for a0, for b0. So this is going to be 0 now. And then for all the other bk's, we're going to plug in 2jak. So I plug in 2jak here, 2jak here. Remember, the minus terms has a conjugate. So now I bring the conjugate in. I'm going to get ak conjugate, and then this j gives me this negative sign. So I have this negative 2j term here and a positive 2j term here. And on top of that, I have this ak conjugate and ak, which prior we just found were the same, right? So these two are the same, and therefore we can just factor out this ak out here. I'm going to take this 4 so that we can have this 2j, so we can have this 2 on the bottom, and then also using the fact that minus j is equal to 1 over j, we can actually bring this j down to the bottom. And the whole point of all that is we can manipulate to get this term here, which is the inverse Euler for a sine, and now you can see that that signal can be completely represented by a sum of sines instead of a sum of cosines. So the flip side of what we talked about just a little bit earlier is that instead of even, when the function is odd, the implications of that, and this is just the definition for function being odd, the implications of that is that the negative terms, the b minus k terms, is a sign difference from the bk terms. So bk is equal to minus b negative k's. And what that also means is that the function can be completely modeled by a series of sine waves. So based on whether the function is visibly odd or even, you'll know whether your summation consists of either sines or cosines. And that can be a good check to make sure that you did something right. Now finally, we're just going to try to do another set of operations to make sure that it matches up with the book. So this is what the book has. It's shifted up, and it's also phase shifted a little bit. So if you study it carefully, you'll see that we bumped it up by 1/2, so it goes from 0 to 1 instead of minus 1/2 to 1/2. And then we also time shifted it by half a period in order to get it to have to be at its minimum at t equals 0 instead of its maximum here. So we're going to write that up. It's going to be x of t time shifted by t naught over 2 to the left, so minus t naught over 2, plus 1/2. Now, this bump up of this plus 1/2 basically means a DC shift, right? Which means it only affects one term, the c naught term here. So c naught is simply equal to a naught plus 1/2, which is equal to 1/2 because a naught was 0 before. So all that means is that instead of a naught being 0, we now have this new DC term. So by inspection, you know that c naught is going to be 1/2 because this triangle wave is DC shifted by 1/2. And then from part C, using what we did in part C, where we know that a time shift is equal to an extra phase shift, or you can use that table that we looked at towards the very beginning, we know that shifting by t naught over 2 is going to be multiplying it by e to the j 2 pi over t naught k times P naught over 2. So you take AK, you multiply it by e to the j omega naught k, essentially, times whatever amount you time shifted it by, which is 10. So we're going to just plug that in. We're going to have this new minus 1 to the k term, and then everything else is just copied for our new ck, and then remember that when k is 0, it is now 1/2 instead of 0. But there's one last simplification you can do. Notice that when bk is not, that when ck isn't 0, k's are always odd, which means that this is always -1. Therefore, we can actually just put in this minus sign here. So the simplified answer is ck is equal to this expression for k is odd, 0 for k is even, and 1/2 for k equals 0. And you'll see that this matches the equation that's in the book. So take a deep breath. You just survived the absolute worst case scenario possible in terms of deriving using method 1. You're going to have something similar in the homework, but it's not going to be as bad as this. And you can we also did some demonstrations in terms of how to derive the effects of the various operations. In the beginning, you'll probably be asked to prove those relationships a few times, like in the homework. But after that, hopefully you can use something similar to the table to just know what tweaks you have to do to find the new coefficients. And that should do it for Fourier series. Good luck, and let me know if you have any problems. If you actually listen through the whole thing, send me an email, because I'm kind of doubting that nobody's really listening at this point. The secret password is llama. So email the word llama to me, and I'll give you brownie points somehow. But I will be very impressed that you actually listened through all this. I'll see you soon.